Okay. So now we're going to see how the elastic curve equation works. Okay. So now we're going to look at a different structure. So this structure is a cantilever beam. Okay. It's a cantilever beam. And at one point, this is our point A. This is our point B. And then we have a certain distance from here to here. It's known as L. Okay. And then this structure is under a gradient distributed load. Okay, so this is a gradient distributed load. And at this end, omega naught is basically the amplitude of the longest arrow. Okay, so this is our omega naught. Okay. So over here, to solve a problem like this, the first thing you have to do is to know your boundary condition. Okay, so we are going to write out our boundary condition. We're going to start from x is equal to 0 at point A. X is equal to L. Okay. And the sequence we're going to go through is V, M, theta, Y. Okay. On the right hand side is also V, M, theta, Y. So you will ask me, Eugene, why is V, M, theta, Y? So V is a shear force. And if you were to integrate the shear force diagram or shear force equation, you get bending moment. Once you have bending moment, this is the slope of deflection. And Y is our deflection. Okay. So now we are going to create our boundary condition. When x is equal to 0, B is also equal to 0. Okay. So if I were to draw our transformation, X and Y. Hold on. Can you hear me? Yes or no?
Yes.
Because all of a sudden my headphone decided to shut down for no apparent reason. As long you can hear me clearly, right? You can hear me, right? Okay, I think okay. So the shear force is equal to 0, and I'll explain to you why, okay? If we see how the structure will deform, okay, so if I were to sketch the deformation pattern, right? The structure will deform this way. So this is our point A. This is our point B. And at point A, at this point where deflection is, or there is a deflection, right? There's a deflection, right? At point A, the fact that it's allowed to deflect at its maximum, i.e., there is what? At point A, right? There is no reaction force. Okay. Whereas at point B, right, deflection is equal to 0. So there is a reaction. Okay, so V down here is not equal to 0. But over here at point A, X is equal to 0. Okay. Now moment is also equal to 0 at point A. Now, let me put in the rest of the boundary condition first. Then let me explain why moment is equal to 0. Slope at point B is equal to 0. Why we know that it's equal to 0? Because it's built in, right? We know that the deflection is equal to 0. So y is equal to, so this is clear. This is clear. This is not clear. This is not clear. Okay. Let me elaborate further. Okay. And this is important. Probably this is taught in 2P. Okay. And some of you, yeah, I've seen this. I can't remember. Don't worry. Okay. Before I go on, we're going to sketch a free body diagram. Okay. So the free body diagram looks like this. So you have a single load over here. Is your equivalent is your equivalent load. So this triangle load, we make it to become one equivalent load. Okay. And this is our point A and our point B. At point B, we have a reaction force known as By. And then we have also a counter moment, okay, which is By. Okay. So this is how our what? Not By, moment about point B. Okay. So this is how our free body diagram looks like. So if we were to go back to our boundary condition, we know V is not equal to what? 0. Okay. When X equal to, we know that the moment is not equal to what? It's not equal to 0 because we have moment at point B and we have what? By. However, at point A, there is no what? There is no force, no reaction force, or bending what? Or bending moment. So that is why moment is equal to 0. Okay. Then let me further elaborate what do we mean by slope. Okay, I'm going to explain what do we mean by slope over here. Okay, I'm going to explain what do we mean by slope. Okay, so the slope is basically, if we were to look at the deflection of the beam, okay, we were to look at the deflection of the beam. So this is how our beam deflect. And then at this point over here, right? So this is our point A, our point B. Okay, and this is where we have our built-in. Okay, let me tidy this up. This is our point B. If we were to look at the slope is basically the tangent to the point. Okay. So if we look at point A down here, the tangent, so this is the tangent. Okay. So when that's the tangent, right? So this is a tangent over here. We know that this is getting ugly. My bad. Okay. So this is point A. Right? And if you look at the tangent, right, at point A, we draw straight a tangent. this is our slope. And if you look at point B, okay, if we were to draw a tangent, right? If we were to draw a tangent, right? This is our tangent, right? Theta is equal to 0. That is why we know that theta is equal to 0 at point B. Okay. So this explains the boundary condition. Okay. So now, how does this elastic curve works? Okay. So how does the elastic curve theory works? Okay. So first, we have to consider the expression that dv over dx, okay, is equal to minus omega x. Okay. So it comes to, what do we mean by omega x? Okay. So we go back to how the structure is been distributed. This is x and this is omega, and we know that we are on a slope down here, and we know at this point we have L and omega naught, right? Why L? Because the distance from here to here is L. The height from here to here is omega naught. So to determine omega as a function of x, this will be equal to what? This will be equal to omega naught over L multiplied by x. Okay. So that is the equation of the slope, right? So note that omega as a function of x is equal to omega naught over L x. Okay. So now we substitute into dv by dx. And now it's equal to minus omega naught over Lx. Okay. Then what we're going to do next is we are going to integrate. Okay. So we have v as a function of x. So this is equal to, we are going to integrate minus omega naught x over L, and this is dx. Okay. So this will be equal to minus omega naught x squared over 2L plus by C1. Okay. And this expression over here is also equal to dm over dx. So we are trying to get our what? Moment equation over here, right? We all know that, right? We are trying to determine our moment equation. So to get our moment equation, what we are going to do next is we are going to integrate again. Okay, we are going to integrate the second time. Now, by the way, I'll be teaching this probably on the last week of the course. Okay, again, but this is, you have to know now, because later on we might apply some of this in bending moment. Okay. So when we integrate this the second time, so m as a function of x, we are going to integrate the entire term minus omega naught x squared over 2L plus by C1 dx. Okay. So we will have the expression minus omega naught x cubed over 6L plus by C1x plus by C2. Okay. Then this whole thing we know is equal to what? EI d squared y over dx squared, right? Because this expression over here, which I'm going to highlight, m as a function of x is equal to EI d squared y over dx squared. We just applied the what? Elastic curve theory. Can you see this? Okay. So this is where we apply the elastic curve